Alright, so we're going to start working on question 18, which is talking about the windward side of a mountain. We're going to be filling in our information on the table mountain that's on the bottom under question 18 for chapter 6 lab. And they give us some information here, and they say that you're going to fill in the space for the temperature and dew point temperature at various heights on the windward and leeward sides of a mountain, assuming that the wet adiabatic rate is 5 degrees per 1 kilometer. So let's put down all of our information. Our dry adiabatic rate is going to be 10 degrees every 1 kilometer, or 1,000 meters. Our wet adiabatic rate will be 5 degrees every 1 kilometer, and our dew point is going to be 2 degrees every 1 kilometer. So now that we know that, we can begin working our problem. Right here we can see this is temperature and this is our dew point, and we're going to cool off as we go up. So 25 degrees Celsius, and we're going to continue to increase till we hit our lifting condensation level, and then we are going to flip our rate of cooling off from 10 degrees every 1,000 to 2.5. When you encounter a problem like this mountain, it's important that you do both the temperature and the dew point temperature at the same time, because when you hit a point where the temperature and the dew point temperature are equal, so they're the same, that's actually equal to the lifting condensation level. So we want to make sure that those things are done together. So I'm going to do the 25 degrees and then the 13 degrees, and I'm going to go back and forth. So 25, and I'm only going to do a half step, so not 1,000 meters, but 500 meters. So I'm going to go down, instead of 10 degrees, only half of 10. I'm going to go down by 5, so that puts this one at 20. And once again, I'm doing a half step, so instead of going down by 2 degrees for the 13 degrees Celsius, I'm going to go down by 1, and that's going to make this 12. I'm going to go down by 5 again, and that's going to be 15. And on this side, I'm going to go down by 1. That's going to give me 11. And then I'm going to go down by 5 one more time and give me 10. And then on this side, I'm going to go down by 1, which is 10. Now notice these are equal numbers now. The temperature and the dew point are equal, which means this is where my wet adiabatic lapse rate will begin. This is also the bottom of a cloud. So if there was a cloud, this is where the cloud is going to form on the mountain. This is the cloudy side of the mountain. So now I'm going to flip to my wet rate, but I'm not going to go down by a full 5 degrees like it says up here, since I'm only doing a half a kilometer in my set. So I'm going to go down by 2.5. So that's going to make this 7.5 degrees. Over here, my lapse rate, as long as I'm making a cloud, is actually the same, but on this set we're going to go down. So since the dew point means the point with which water is going to come out of suspension, if it's coming out of suspension, both the dew point temperature and the temperature of the cloud will be the same, because it is water coming out of suspension. So this is all cloud on this side, which means this is also 7.5. and this is also 5. Which brings us to the funky catch. When I get up and over the mountain and I begin to descend, as you go down in altitude, you're going to warm up, which also means the water is going to stop making a cloud. So it's going to warm up and stop making a cloud, which means that this side is going to dry out and warm up and become the dry adiabatic lapse rate again. So this is DALR on this side. So I'm going to go from the 5 degrees that I ended up with on this side, and I'm going to warm up my air by a half step of 10 degrees. So instead of 10, I'm going to go warming up by 5, and I will get 10 degrees. This goes back to my dew point rate over here, So it's going to warm up, but it's going to warm up by a half step of 1 degree, right? Now notice this time, instead of the little half steps, instead of half a kilometer, we're going to go 1 whole kilometer, which means that we're going to warm up by 10 degrees and by 2 degrees. So that makes this one 20, and that's going to make this one, so this was 6, and what's going to make this one 8. And over here, this is going to be a whole step again to get to sea level. So this is 30, and this is 10. All right, and the example that you're looking at on this page is pretty much what happens on the West Coast all the time. The air goes up and over the mountain ranges, and then once it gets over the Colorado or the Rocky Mountains out on the West Coast, you end up with the desert, the Mojave Desert on the other side, which is dry air, because we can see the dew point temperature of 10, and very, very hot at 30. So this example is exactly what happens on the West Coast of the United States. Questions 19, 20, and 21 ask you things about that mountain range, and so you just have to answer your lifting condensation level for 19, 20, which I've already sort of explained, and 21, I've sort of explained what's going on the West Coast that brings you to your answers. Please take a moment at this point to take a look and read about the atmospheric stability and what we mean by a stable atmosphere, and that'll help you get through the next portion of the lab. All right, so there's a bit of a mistake in questions 22, 23, which is that they ask you something in question 22 that you can't answer till you fill in the table question 23. So please fill in your table on question 23 first, fill in this table below, and then go back and find the lifting condensation level, which is where the temperature will be equal to the dew point temperature. And remember that your dry adiabatic lapse rate will be 10 degrees Celsius every 1,000 meters. And your wet adiabatic lapse rate is written right here, and that's going to be 5 degrees every 1,000 meters. And your dew point is 2 degrees every 1,000 meters. And since this is very similar to what we were working on in the question 18 with the mountain, except for this time you're going to be just rising up in altitude. Make sure that you're always looking at your heights and altitude, and then working your parcel of air and your dew point for that parcel of air. This time the only additional catch is you're going to be comparing it to atmospheric stability, and that gives you your environmental temperatures, which are right here. The final step after you fill out this table and answer where the temperature and the dew point temperature meet, so this relates to this part, is to map it. You're going to graph over here the environmental lapse rate line, the dew point line, and the line for the actual air parcel. It should look like a set of lines that are going to be cooling off and going up, and that will help you then go back and compare to the examples that you're looking at on these pages regarding stability of the atmosphere. And since this part of the lab is sort of repetitive to what we've been doing throughout Lab 6 and some of 5, I feel like you guys can work your way through it. The final part is, if you're looking at a whole lot of clouds and they seem to be conditionally wet, could you be looking at a forecast of a thunderstorm? And so question 25 is your opinion after you've finished graphing and drawing in the lifting condensation level. Be sure to be accurate to your altitude heights when you're putting in your dots for your points. And remember, you're going to be putting in your lines, very similar to these images, where we should be seeing the air parcel and the environmental lapse rate. And you can do your air parcel as a dashed line, and that's going to actually change curvature, where it will start cooling off and then it will become more broad and straight up, and your environmental lapse rate should be really consistent as a line straight through. So I'll allow you to graph, and best of luck completing your lab.